was a kid, believing your stories, the things that you did. Now I'm asking for my money back. I have it tallied up, 800,768 fiat dollars. Gave you my trust, followed your way. Now I see though deceit on display. NASA, you've been lying to me. Lies and deceit, it's all I see. NASA, you've been lying to me. But deception's a game played every day. Lies and deceit, it's all I see. NASA, you've been lying to me with your fake streams and false reality. NASA, you've betrayed my trust with your fake streams. I stopped being blind, admit your unjust lies. Since I was a kid, you fed me lies, stories and fables. Now I realize, meant for the masses, to be force-fed to the blind.
Introduction here. We're going to cover tonight the methodology. I'm going to talk a little bit about my experience taking measurements and stuff, so we can more share the process and make it accessible to people that want to participate. And then we're going to get into some questions and answers. Mike is here for a little bit, so if you have questions for Mike, this will be a great time for that. If we run into something that's going on for quite a long time, what we'll do is we will write that down and get back to it in the form of a PDF, and we'll answer that more in depth on the next update or whatever, or we'll come back to it and recap it, kind of thing. So we'll take better notes from that. We'll go over a PDF note exchange from Jesse and Mike towards the end, and then we'll also watch a couple of clips from Jesse and McTune's stream where we're going to correct a couple of things regarding the celestial theodolite measurements and methodology. Okay, so Goose, if you guys want to tune into the stream here, Goose is now live with his video. He's going to explain what's going on here. Actually, I can give a quick recap if you want, Goose, or a quick intro.
No, I think just jump right in, right?
All right, go ahead and send it.
Unless you had something in mind.
No, I just want to say that a big part of the premise of the celestial theodolite, right, is that the occlusion is a physical process with the relationship of the light source and the physical object that is doing the occluding. So at that intersection point, it has to be physically real. It can't be apparent. So this is going to be a good demonstration and introduction into solidifying our position.
Mm-hmm. Yeah, exactly. Okay, so what I'm showing here, or this is like a little Cell 3.0 rig that I built just in my shop here.
We're supposed to go on your stream.
Yes.
Yeah. Okay.
Oh, can you see it?
Yeah.
Oh, okay. And then up here on the upper left here, I built a little point source light. So it's just a cardboard box with a little tiny hole punched into it. And there's a flashlight sticking in there. And then this arm here, it pivots basically back here, and it just moves in an arc along this pathway here. And then I have two dowels here. So this is like the peak occlusion dowel, and then this one back here is just to line up the camera basically. And there's a little I have a little GoPro sitting back here giving us a visual. Everything's like on a horizontal plane, but just imagine it flipped 90 degrees vertically. It's kind of the same for if you're doing like a real life occlusion. So, let's see, where are we there? So, okay, so right here, I've lined up our light, our point source light simulating a star. I've got my straight stick here and this angle. So it's just showing that basically we have everything lined up here. then, let's see, I think oops. Hold on, go here. So then, so right now I'm just basically doing like an occlusion here. And right there. So this is the point where you would be stopping your stopwatch, checking your video stamps for timestamps, and then heading back to Stellarium. Get your angle, your angle to the true position of the star. Okay, so now we're introducing a refractive element. And what's going on here is this is just a little rectangle, plastic rectangle I found to fill up with water. And in the middle of it, there's a dowel that's been glued to the bottom of it. And that dowel is centered right on this hole here. So you can see me pull. So popping out that our first dowel, our alignment dowel, centering the refractive element on there. And then we can have a look. Even just putting that refractive element has brought. I haven't moved the occluding or the star yet, the true position of the star yet. And you can even see there it's brought the star into view. Now I'm just dialing in some refraction here. Okay, and now we're going to do a refractive occlusion. So if we're having like some celestial refraction going on here. And here you can see the light. And moving it, and boom, it's gone. Now we will remove this guy, stick our alignment peg back in there, and put our straight stick. And now, what you may notice is the true position of the star has shifted. This is basically, you can think of this as time. So you could say this is an offset. This is like it's kind of arbitrary at this point, but so that you could say this is time 0. And grab my thing. And this would be t time plus 10 seconds, or time plus or minus 10 seconds. This works going both ways. So if we're doing a rise as well, it would just be opposite. So now our true position would be do the math. Let's see, minus. It would be a minus. We would be seeing the occlusion sooner. All right, we would be seeing it. Oh, there it is.
Nice.
So basically, the point of all this is just to show that with a refracted light beam, you still need that physical occlusion to
match.
Block it. Yeah, the physical occlusion is going to. So if you have a refracted light beam, you require physical occlusion to block it, and the consequence of that is a timing difference. Right there. And this timing difference is in relation to the true position of the star. This is what we're We're reading out a stellarium. It's yeah. So that's kind of based on, you know, like sidereal time. Every second of the day, that the stars are rotating above our heads, and there's no way to stop it. They're moving.
They're just gonna keep going, right?
They keep on going. Yeah, it's basically, you could almost just say that it is our time. Time's kind of an interesting thing once you start looking at how they do time and what it's referenced to, and how they make it meaningful. Any questions there?
So this is just like an example, right, of something that everyone intuitively, almost common sense understood, but just to hammer it down, sort of here you go, demonstrated sort of thing.
Yeah, exactly. Yeah, it's
Yep.
just like, here it is. I mean, refraction. Even if you have a bendy light, you still need something to block it
Physically, right? That's the point.
physically. Yeah.
So
And
that when the
then,
star goes behind the mountain, it's actually going behind the mountain. It's actually physically being obstructed, no matter what refraction you have before or after. It doesn't matter.
yeah, and then also,
So
sorry.
On the,
real
on the
quick,
proper scale, right?
real quick, hold on, Funny, real quick, because this is extremely important. So what Goose was talking about earlier with time and how this relates to the celestial theodolite analogously, right, is the stellarium, right, celestial navigation, the globe model, all that celestial terrestrial sphere model is all tied to the positions of the stars at a specific night and time, right? So on the vernal equinox, there's a snapshot of the position of the stars taken, and then setting everything to move at 15 degrees per hour with respect to Greenwich. You, if you know what time you're at, you know what angles the stars are at, and vice versa. So what the relationship is with the geometric occlusion using the calculated true geometric position, which is that true unrefracted position that would just be like, you could consider it the light source moving at 15 degrees per hour with respect to time, and then whatever your time is, that's where that true geometric position is going to be, not the apparent position, right? The star that you do see. So that's the relationship there with the angles and time equivalents. Go ahead, Fundy. Sorry to interrupt. I just wanted to hammer that point home there.
Absolutely. Yeah, I was only going to point out that uh, on the full scale, scenario, compared to like the scale down model, it's not appreciable or anything. It's not a big deal, but there's just the slightest bit of you know give on
No,
how
it's significant.
precise it would be, right?
No, it's significant. Extremely significant. I'll show you. I got the Desmos where I've basically drawn everything to scale, and you can see like how much time is actually required on a refracted star, even one that's like 0.55 of a degree higher, like off of the true star position. One sec, I'll just switch screens.
Boy, Goose coming in with the 2 scale there. Very nice.
So it isn't realistic to say that in the on the true scale of it actually happening, that straight edge 2x4 there wouldn't have the most subtle bend in it.
Oh, yeah. I mean the rig itself, that's not to scale. Like that's just showing like the underlying concept. There's
Well, I guess what I'm
no.
saying is that when you're looking over the peak of a mountain, and let's say it's a rising one, right? That
Mhm.
you could see a star rising above the peak of the mountain, and like geometrically, the star you're seeing over the peak of the mountain might not actually be a straight line that you're seeing it to. That is actually an extremely subtle curve. that it actually hasn't risen to that straight linear viewer point A, point B, peak of the mountain, and then point C would all be 180 degrees. That you might
No,
very
we're
subtly be
seeing
able to
them.
see point C a little lower than 180 degrees.
I think we're seeing these stars dead on. Honestly, there's no there's no such thing as celestial refraction here because we're using we're referencing like the time clock. So it's a non-optical reference that we're using.
Wait, what? You think the stars are traveling? You
Yep.
think the
So let's
stars are traveling straight, like the Globers think that?
so show us this 2-scale diagram that you made here
Yeah,
real quick to show
sure.
the
Let's jump into that.
significant difference here.
Yeah. So what I've got here is I think this is one of Jesse's measurements. I think he likes this one because it shows like it's a nice kind of like globy looking result here. So what we have here is we have a true star. So the true star, this is the geometric star lined up with the globe peak here, and then we have a refracted star up here, and this refracted star is using the same. It's using the same exact, like this is basically Jesse's spreadsheet that I just borrowed I just kept all these equations in here. So this refracted star right here is using essentially the same refraction. I can, yeah. Where is it here? This is the anyway, I can look at that later.
So what you're showing there, though, is that at the time of occlusion, the globe was predicting that the apparent position of the star would be higher than the mountain.
Yeah. So what we have here is like we've got a true star occlusion, and then we have an apparent star occlusion up here. So the Globers, they think celestial refraction is a requirement for this measurement. We have to take into account the apparent position of the star. So when you're looking at this image here, we have like an occlusion up here. So you can imagine like this peak, like if I made this peak a little taller. Oops, not that tall. So say it's something like this. And you can see like the apparent star being, so what we have, so you have the globe down here, right? And then you have a apparent star location being occluded up here, and we've got basically have two problems here. So we have, if the star is being, so keep in your head the physical occlusion example that we just gave. So if the star is being refracted upwards and is being blocked by a physical occlusion on a flat Earth, then that's up here, right? There's the globe would be down here. And then there's also the other problem that the timing difference. So our true star timing difference is actually down here. There's going to be like there's a timing difference between this and this because like as the star is coming down, right? Like on a flat Earth, we're going to stop it like right here. That's where our clock would stop. On a globe Earth, if we were getting globe readings and it was an unrefracted star, we would stop it here. But since we really want to claim that there's a refracted star, we're still up here. So what would really need to happen is for a globe measurement and a refracted star, it needs to come all the way down here. Hold on, I think I just got to fix my mouse. Does that make sense? Sorry, I kind of
Yeah, so you're saying so the globe measurement requires you to like temporarily disregard celestial refraction when you do that.
Yeah,
Like
well,
you're
the
using
globe measurement, they it's all about the apparent star. Like that's what's being refracted when we're
oh
looking at Jesse's
well yeah like
Jesse's.
in all
But
the other distances like that's where they try to co-opt the measurement timings right through the
yeah,
refracted. But here in the instance where it was done with the true geometric position with an elevation and distance that matches the quote unquote globe, this timing this requires you to ignore celestial refraction for this because otherwise it's way above the mountain, right? Is that's what you're showing?
yeah, basically, like because it's always reference to the true star.
Right.
So if it's up here, like our timing, like the clock is going. So basically, this you could look at the star as almost like a clock hand, and when it gets here, you could stop the clock. But that's not where we want to. That's not where the globes wants to stop it because we're dealing with the parent star location. So they need to stop the clock down here. Sorry, it's the Desmos is a little bit jumpy. But let me fix this for one quick second here.
I do have a dumb question. Should I wait until the end?
You can go ahead and get it in real quick.
Okay. If the radius is much larger, like say if it is some kind of chunk, right? If the radius was quite a bit larger, would it not give closer to the readings of the true readings we're getting here, even counting the
Well, the thing is, when it comes to the globe's dimensions, it has to be exact because that's how the coordinate system is defined with respect to time and all the angles to the stars. So they're not allowed any sort of like radius extension unless it's in the form of refraction. But because we're dealing with the geometric position of the star, right? They're in a precarious situation here because there's no allowances for said increase in radius because then that would affect the entire night sky.
yeah, I mean that's kind of what I was getting to too with my calculations is like depending on how much larger it could be. I wasn't even looking at this stuff that you guys are sharing though. So this is a different perspective that's kind of showing basically the same thing basically.
Yep.
Mhm.
Nice. All right, Goose, did you have anything else you wanted to add to that?
Yeah, just really quick. I was just looking, so I just kind of set it up here for Jesse's. See this green line right here? This is Jesse's sim angle. He used to call it the Heffron angle. So you can see it looks pretty good here. We're hitting this peak real nice. But the issue is our true star is down here, and this is what we're referencing time wise. And if you look over here, this is basically like real seconds. This is like 240 seconds per degree. You can break it down. You just break time down 360 degrees, and then you can bring it all the way down to seconds. But yeah, so basically they're about a minute and a half. So if they were coming this way, they'd be a minute and a half. They still need a minute and a half to get this reading because this is where we're referencing, and stellarium is the true star position down here. And then if we're doing a rising star, it's the same issue. It's just a minute and a half sooner we would need to get that
And that's
apparent star.
aligning the refracted position, the so-called refracted position with the true, like where it would have to be if that was the case.
Yeah, this is using like the same refraction value and coefficient
Right. Got you.
that Jesse's using. It's kind of like once you get into like less than 15 degrees, shooting across the horizon in a 15-degree window, you use this fancy
Right.
refraction algorithm that they've created.
Awesome.
So yeah, long story short, if I was Globers, I would probably really want to drop that refraction argument.
They can't.
They can't.
But their
It is
measurement, like, look,
super
it
locked
helps. It helps
this-
them in this one. In this case, it would totally help them. But if they're really stuck to that, then they're gonna need another occlusion a minute and a half later or earlier. Then you can call this time 0, T0, and then yeah.
All right. Well, if there's nothing else on
Any
that,
questions?
or any more questions, we can move on to the introduction that I was gonna the little overview I was gonna do, because the refraction thing heavily played into the premise or whatever. So it worked out really good.
Nice. Yeah, I'm all done.
All
All right.
Just have my mic muted. I'm taking everyone's silence as agreement that we're gonna move on.
Correct about everything?
Yes.
That's an
All right,
agreement.
Shane, if you could screen share
What am I sharing? PDF?
the Canva link that I sent you.
Canva.
All right, and if you guys could switch streams from Goose's to Shane's. Okay, so the premise is pretty straightforward. We're referencing the true geometric position of a star and the raw calculated uh, elevation angle to a mountain just based on plane trigonometry, and then we'll subtract what the globe would predict for the drop over distance for that elevation, and we will see if stars that are aligned with the true geometric position of the mountain and themselves, if they're aligned at the same time at the peak, will the star be occluded for an observer at the calculated distance away to get that relative angle to begin with. So the process is pretty straightforward. You can use peaks that are to the east or to the west. So star rises or emergence, or you can do occlusions where they're setting into the peak. The best way to do it is to have your camera centered straight on the center of the peak. If you can go for direct peak shots, that makes it great, because the elevation is going to be pretty much what you're going to be able to get out of Google and all that without having to do any other sort of cross referencing and whatnot. So if possible, direct peaks are preferred, but you can always you can always go out of your way to figure out the exact elevation and stuff after the fact, and we'll kind of go over that a little bit as we continue. Okay, so next slide, please. So this is following up on the refraction and occlusions. So only when the physical object is intersected by the light source is when you actually get the occlusion. You can skip to the next slide, Shane. This is what the camera view of Goose's video that he was showing earlier looks like. So when he was showing the topographical view of what we were looking at there, where he was laying out the positions of everything in the alignments, this is what we're looking at. So if you could, so this is in air, and then this is the top view. So we see the string stick that he's moving, the light source with, and then now he's added a medium over top of it. And this is what it looks like from the camera angle. As you see, the image sticks around a little bit longer, and it's not occluded until the physical intersection point happens in reality. And then when he gets to the topographical view again, you can see the angle difference of the true position of the light source, showing that it doesn't matter if there's refraction or not. We're still going to get two mutually exclusive outcomes out of this process, because the occlusion is physical. And so
Yo, this is awesome. This
so
is an excellent
yeah,
example. Wow.
dude, it's so great. And then so you can I think that's it. So you can skip to the next slide. So here's tools and things that'll be useful for, actually, I can pull this up on mine and look at it from here. Okay. So here we have tools and things that'll be useful for finding the peaks. So that there's an app called Peak Finder, and you can also use it in your phone's browser if you don't want to download the app or whatever. It's like $5, but I highly recommend it. It's definitely worth it. And you can actually enter your coordinates here, export the peak silhouettes for Stellarium. You can import them later for analysis and stuff like that. But more importantly, you'll have a nice overview of what peaks you're looking at with a 360-degree view. So you can turn to the east or west, and then all the peaks will pop up, and you can click on each individual peak if you're on the app, and it'll tell you the relative distance and elevation based on where you're at. So you can use that as a great reference for what you're shooting at or what you're trying to identify if you're doing it at night or if you're doing it in the day and you don't know the area that well or whatever. So here's kind of what that looks like when you're zooming in on the peaks. So let's say so what happened to us in our example that I'm going to show you guys here is we were off the peak by a little bit. So when you go off of the side there, the elevation changes. So you can verify that on Google Earth later and like get several different references and stuff to kind of narrow it down if you need to change the elevation if you're off the peak by a bunch, like if you're on some ridge on the side like I was. So when you get into recording the data, there's going to be necessary information that you have to record. The primary, most useful information that you need is your coordinates for where you're starting and the coordinates for what you're looking at. Everything else you can backwards derive after using calculators and fill in for a spreadsheet that you could import to other spreadsheets and stuff later on. I have a link here for a custom data collection spreadsheet that I'll get for you guys. But because the celestial theodolite one is constantly changing, it's always updating, it's an ongoing process. So if you don't want to stay up to date with the new spreadsheets and whatnot, it'll be nice to have your own data collected. So there's a thing that you can reference for that. I'll give out. It's a little template. But anyway, after you have your coordinates, you can use that to figure out the difference in elevation between you and the mountain, which you can use to derive the and the distance to the mountain peak as well, and also the initial and final bearings, which come out of the computation of your observer coordinates and the peak coordinates, so your target coordinates. So if you do it in that order, you will get the initial and final bearings, and the final bearing will be where you're going to be looking, like the direction that you're going to be looking in Stellarium when you're trying to find the stars. If you don't already know the star. So let's see. Anyway, so the time of occlusion is also important here. So you're going to want to have the exact time that the star occluded, because that's going to correspond to an angle. That's what you're going to be looking up later. And then you can write down the azimuth and the elevation angles of the stars when you're done for your data sheet. But highlighted here in pink is going to be important information to write down. And then the green stuff is the calculated stuff that you could get after the fact. All right, for the predictions. So when you go into Stellarium to look up the stars, what you're going to do is you're going to adjust your bearing to that exact location. So, oh shoot, is it changing slides with me, Shane?
Yeah.
Oh, perfect. I was going to say, dang, did I just go through all that and then
No, I
nothing?
figured that you
Okay.
switched to your own version, that you had no idea what we were seeing, but I was keeping track. I think we followed along nice.
My freaking guy. All right, cool. Okay, so we're on slide 7 to be clear. Okay.
Yeah. Stellarium
Okay.
slide.
Yep. Okay. So here we're looking up the time, and we got our coordinates for the peak. We're looking up we got the time and date, and then we're looking at what stars happen to be at that angle. When we find the star, we click on its name, and then it identifies itself. It gives all the Pokemon statistics here on the side, which you'll write down and use to verify the geometric relationship. So to turn off refraction, all you need to do is click on the remove atmosphere button, I think, or you can just press A on your keyboard. It'll turn that off, and then that'll reference that true geometric position. And again, the true geometric position, if we could scroll over to slide 13, Shane. Okay, everything that Stellarium is referencing, the quote unquote globe, celestial navigation, latitude, and longitude, well, all of these things are referencing is a specific point in time for the position of the stars. And that is called the first point of Aries, right? That's a snapshot of the sky on the vernal equinox. So every star has a zenith position that corresponds to a ground position on the vernal equinox. Moving at 15 degrees per hour, you can calculate where that star would be with respect to your position. So if you know the star name and the angle, you can verify and you can figure out what time you're at, or vice versa, using the stars to find your location. So all this is doing is taking that snapshot, tying those locations to an observer at the center of a ball, a fictitious sphere with a radius of 3959, so that they could do their calculations between the celestial and the terrestrial sphere. So,
Hi.
1 second, we're in the middle of a presentation. Please mute
Yes.
unless you have a question towards. Um, so anyway, just wanted to show what exactly that's referencing there. So anyway, when you know the time and the angle, or when you know the time, you get the angle. That's what all that corresponds to. So when we're referencing that true geometric position, you could pretty much know with certainty that that's the right time for that angle, because that's going to correspond to how people figure out their latitude and longitude. So here on slide 8, we have the data log template. You can use that there, or you can use the calculator there once you have the necessary information from slide 3 to calculate the angle differences, which to get that, you're going to need your observer elevation, the elevation of the peak, and you're going to need the distance in kilometers for that calculator, but it'll give it in meters on the output thing. But anyway, you just enter your distance there, and then that'll give you the trig functions for the flat Earth prediction and the globe Earth prediction. And then you can also see what the refraction correction applied would give. And what you'll notice when you start entering in different values for these different scenarios, what you'll notice is if you just apply celestial refraction to the raw globe angle, it almost always makes up the difference to the flat Earth angle within an arc minute or two. So let's see here. So now we can move to slide 14. Oh, I'm sorry, wait. Move to slide 9. And if you could play that video out. Okay, so here we're looking at an occlusion. So we got the timestamp from when the video started, and then we could count the frames to when the star gets occluded to figure out what time it was. In this case, it came out to be, I think it was like 2 minutes and 25 seconds or something like that for when it was occluded. So the timing comes out to be, what was it? I forget what it was off the top of my head, but it was like 37 minutes or something like that. So you just add the time in which it's no longer there with the time that the recording started, and that's how you get how you can find the position of the star. So then if you go to if you go to slide 10, you'll see I have 2 images here. So this is an image of the location during the day, and a location and a screenshot from the sea star that did the recording there at night. So what I do is I go to slide 11, and then I super zoom in on the daytime image so I can get nice clear outlines of the silhouettes of the peaks there. And then I scale down the sea star video until it lines up with until it's like to scale with the peaks, until it makes sense geometrically. And then I just slide left to right until I find a spot that it looks like that's where it was at. And what it turned out to be was, I think it was right around here. If you turn transparency on and off, there you can see these line up pretty good. And because I shot we changed directions at night, so we didn't actually know the position where we were facing from where we started. So this is how we figured it out. This is how you would figure that out through this process. This would be some of the steps you would follow through with. And then you can come back through here. You can go back to that peak finder website with your coordinates entered, and it'll say, for us, it had 3 peaks right here. This one turned out to be Getaway Peak. And then this is a ridge that goes down here. That's about 200 or about 100 something meters lower than the actual peak. So this is how you can narrow out your elevations and figure out all that stuff when you have to backwards derive everything. So if you wanted to, right, you could just go out, shoot different peaks, record your coordinates, and then record the coordinates of the peak you're looking at, and then you can figure out everything later after the fact. So let's see here. And that's kind of what we've been doing. Okay, so if you go to slide 14 here, earlier when I was talking about the geocentric coordinates and that reference of the position of the stars at that time using a radius of 3959, what they're doing here is they have a radius of 3959 for their terrestrial sphere model, but they're referencing the celestial sphere, setting the altitude of the celestial bodies to 6210, which is just nautical miles multiplied out by the latitude lines. So if you were to follow this out from the North Pole to the equator, the latitude lines 90 times 60 nautical miles would be 6210. So this is also the altitude of the exosphere, interestingly enough. And the model that we were looking at earlier from Goose, if you model the stars out to the to have their true position, like, you know, let's just say hypothetically they were at an altitude of 6210. Well, it's like everything works to scale with this exact representation to how it's being used with the distances and stuff. So this works like completely equivalently. And keep in mind for the, you know, mainstream globular uh, cosmology with heliocentrism is that the stars are like, you know, hundreds of light years away, and you know, and all that. So just setting them to an arbitrary 6210 for the use of this, where the star is going to meet the 69 mile per degree relationship, that is the output that you would get. You would get a celestial sphere that has an altitude of 6210. All right. So moving on now, we have slide 14, or I'm sorry, slide 15.
I got a
This is
question real
from the-
quick.
Go ahead, sir.
So with the 6210 arbitrarily put there, just as if, you know, their celestial sphere, they're basically using like an infinite distance to the star, essentially. That's why you're saying it's equivalent?
Well, no, they're using 60 miles per degree or 69 statute miles per degree times 90 degrees of separation between the North Pole and the equator, and they're calculating that out specifically, right?
Yeah, it's
But
not
yeah.
necessarily arbitrary. It's arbitrary to the limit where the 69 degrees holds true. That's
Yeah,
what they've
the
based the
maximum.
coordinate system on, between those angles of, what is it, 25 to 30 or 25 to 70, something like that. But it's arbitrary in the sense that in their model, like they believe that they're hundreds of millions of light years away, but then like they could, but for the usefulness of latitude and longitude and cell nav, they're setting them to 6210. So it's like
Gotcha.
so yeah, it's like not arbitrary. It comes out of that relationship, but it's arbitrary in that sense. Okay, so slide 15. We have we're going through a celestial guide manual here, and this guy is talking about the horizon system of coordinates, because we often say that we see in a dome of vision that the hemisphere of the sky is projected into our dome of vision, and we're told that we just made that up. Well, the easiest way to teach celestial navigation and to break this stuff down is to define this horizon as a system of coordinates that's made up of the sensible horizon, which is what you optically see. This intersects with your eye, and the geoidal horizon, which also at a distance intersects with the celestial, or I'm sorry, which intersects with the sensible horizon with refraction. So you'll never be able to distinguish the sensible from the geoidal, but you know, there's definitely two different ones. Trust us. And then the celestial horizon here is the night sky from the North Pole to the equator. So essentially one entire hemisphere when it comes from if you're looking up at your zenith to where the sky intersects the ground, that's one hemisphere of star vision. And then the ground of the stars is what you see is what would be for the geoidal, or for the sensible horizon. So that's not something we made up. That's literally the backbone of how celestial navigation works. And as you see here, we have a cross line here with a center point. So this center point is going to be the intersection point where the two coordinate systems, the celestial sphere and the terrestrial sphere models, intersect. Because if you're going to do transformations between two geometric objects, you need to have a common point of intersection. Your z-axis point needs to be aligned. Guys, guess where the intersection point is for the celestial and terrestrial sphere models? It's at the center of the radius of 3959, which we saw on slide 15 there. So when we go over to slide 16, we're looking at the celestial sphere model, which is the separation, right? Like as if we're going to pretend this is a different model or whatever now. This is the separation from the coordinates that make up the horizon that we were talking about earlier. Now for this model, this is where everything is set to that 6210. So when people say, what's the altitude of the sun? What's the altitude of the moon? What's the altitude of the stars? Well, if you were going to do cell nav, right? When you go to do a semi-diameter calculation correction, guess what? You're going to be setting the sun to 6210. and comparing where the observer from the center of the Earth would see it, and taking the difference from that for your correction. So that's the backbone of how this works. So we have this model here that intersects at the equator with both models, right? So both hemispheres are represented by one set of stars for an observer in their respective hemis, and then they intersect, or they this intersection point here extends out from the equator and then goes out to 6210 surrounding the Earth, and that's where the position of the stars are. So when you take their zenith measurements and they're transform those to geocentric coordinates, which was referenced in slide 13 there from the supplement nautical almanac, and the explanatory supplement for the astronomical ephemeris and American ephemeris and the nautical almanac. We can kind of see what they're doing here. So they have a bunch of lads positioned all around the Earth, making zenith measurements at a specific time, so they can lock in the position of a star to relate that to a ground position. And then if we go over to slide 17, we can see that by tying it to Greenwich as the 0 longitude point, right, we can calculate 15 degrees per hour where all the stars are going to be in reference to that original snapshot. And this is, again, has to be tied to the fictitious observer at the radius of both the celestial and the terrestrial sphere. So let's see.
So I have a question. I have a question.
Go ahead.
Are you saying so you're saying they do did you show, like, did you show anything that says that that's what they do for that, or are you just saying that you figured out that that's what they do?
Well, that's exactly what they do. This right here in slide 13, if you read from it, it says the apparent place of the stars is the geocentric position. And this book that I referenced is all about converting geocentric coordinates to geodetic coordinates, which is what Stellarium is doing. So to reference this geocentric position here, this is the ideal snapshot for the first point of Aries. If you look up first point of Aries, you can read about what that is in terms of celestial navigation and how it relates to latitudes and longitudes. But anyway, it says here, refer to the true equinox at the equator date, which is where the star was observed. So again, on the equinox, they're making their zenith measurement, and because the zenith measurement has the least amount of refraction, they're considering that like the most accurate way to relate the ground position of the star in terms of, like, if you were to try and make a 90-degree triangle out of things, they're saying that zenith position would be like the where that lines up at to make that right angle. And then okay, so hopefully that answers that question. And
But do you have anything else? Do you have anything that they say about the 6210 that they're using that? This
Yes. So the geocentric coordinate transformation is setting it to that observer there. And then if you multiply out the latitude lines, that's what it comes out to. So like that's kind of the logical implication. They don't come out right and say that specifically, but that's what the math represents. That's what and that's what the transformation would dictate if it were to work in the way that they're saying it is.
Well, and they
All right,
do claim
thanks.
the distance from the equator to the North Pole on the globe is 6210. So from the center, that would be that arc angle, from the zenith all the way down, like a quarter of the circle. Because they claim that's what the distance is, yeah.
So 1/4 terrestrial meridian.
Yeah.
Yep. Okay. No, you're good.
I just wish you wrote it somewhere, because I can't steal, man, what the fuck you just said.
Okay. So in order to use their latitude and longitude coordinate system, they have to reference a position of time for where the stars were, right? Because that relates to a ground position. Does that make sense?
Yeah.
Okay. So once they have a collection of these snapshots, they now need to make them so that other people at different times can reference where they're at. So we can take our time and look up where that star would be using a 15 degree per hour relationship. Does that make sense?
Yeah.
Let me try again. So using the timing difference from the original snapshot, we can figure out where the star's zenith position is supposed to be. Does that make sense?
Yeah, I'm listening.
Okay, and in order to do that, to make that comparison, right, we have to use that fictitious observer to set the altitude so that we can have that relationship on slide 14, where the star's position represents an angle and a distance. So in order to have all that, the geocentric coordinates is what they call them. Those original zenith measurement snapshots have to be tied to the center of the ball, and then the way that the observer would see the stars move around them is shown in slide slide 14. Does that help clarify things?
Yeah, I think I got it more now.
Okay, cool. All right. If you have any other questions or whatever, I mean, feel free, because it's an extremely important concept to understand, because it is the crux of it, right? Because later on, one of the biggest critiques we get for the celestial theodolite is we're accused of moving the observer to a position where he isn't, and that's not the case at all. And then when you look at the backbone of what the globe even is, it's the merger of two conceptual models, a celestial sphere and a terrestrial sphere, that have to be merged together at a specific point in time for it to be useful. So it's like the epitome of calling the kettle black, or whatever you would say, whatever the thing would be. So to kind of breeze through the rest of these, because I don't want to take up the full hour. I want to get Mike in here to get his update in. Um, that is the long and short of what stellarium is. And then when we get into the celestial refraction corrections, we have um, how they go about how they derive their coefficients, right? So they have where the stars should be to relate to their idealized position with respect to 15 degrees per hour. But when they get lower in the horizon, they end up hanging out a little longer. So to maintain usefulness of the coordinate system, to explain the angles and the times, to make it all make sense, so that they're in the correct spot instead of being in the 15 degree per hour spot, they come up with a way to fit the data, or they come up with a curve fit by integrating the data and using computational models that assume static conditions, so that they can just kind of like generalize it out, see what the difference is, and then have a Excel spreadsheet essentially plug out what the different, or what coefficients would be used to make the star be at the correct location at those angles. Okay, so we can just skip through, if you just want to breeze through 22 to 24, Shane, and just kind of show those. I just summarized what the math is
Yep, I
describing
got it.
there. Okay, cool, cool. And then earlier I talked about the parallax and in the semi-diameter correction. So like setting the altitudes of those bodies, that's what that is in reference to there. So you're invoking that fictitious observer and what he would see for the positions of those celestial bodies, and then you're taking the difference from that to come up with your correction there. And then if you skip to slide 34, this is in regards to moving the observer to where he's not. Well, if we take a quick quiz here, we can quickly determine that the conceptual use of the celestial theodolite is not moving the observer where it's not. It's not strawmanning the globe. It's testing geometric predictions of the globe based on the 15 degree per hour relationship. So if we're using the peak as our crosshair for our conceptual theodolite, we're not moving the observer or doing anything crazy or anything out of the ordinary here. So you wouldn't conclude that a man looking through a microscope is at the end of the microscope as the observer, right? That's preposterous. He's standing right there in the lab. If you go to slide 35, you wouldn't conclude that the man in the submarine is at the top end of his periscope, looking out above the water, right? He's obviously down below in his submarine, and then the crosshair is just the reticle at the end of his telescope there. If you go to slide 36, you'll see a lad looking through a theodolite. Well, he's where he's standing looking through it. He's not standing through the theodolite looking through that end of the lens there, is he? Right? So when we go to slide 36, now we're going to start applying this to observations to the sky, and we're going to increase the length of our apparatus a little bit here. So we have a larger telescope, maybe an observatory or something like that. So this doesn't mean that the observer is at the end of that telescope, right? He's down here looking through the eyepiece. Same exact concept with the celestial theodolite shown on slide 38.
There is only one thing that bothers me about this. Uh, Not that I don't appreciate how much this accounts for all sorts of things in a controlled fashion, and not to dismiss how profound the alignment.
Yeah. All right. Mike, do you have anything that you would, or I'm sorry, Mike, do you want to get to your update and specifically regarding the update to the calculations for right ascension and the J value? Because that was a big thing that we didn't have time to get to last time, and it was kind of interrupted several times when you were trying to go over it. So maybe we can go over that update now if you're here.
I'll be happy to. I've got to figure out how to pull this off. I'm going to try sharing my screen. And on this stream that I'm sharing, this shows the right ascension and declination equations from last week. And I crossed off that calculation at the bottom for azimuth. That shows what the old calculation was. And the problem was there was a quadrant ambiguity error with that equation, and it didn't show up until the 49th star that we entered into the log, and that's when we realized there was an ambiguity. And this slide shows the actual correction for that. So it's it's a although it looks radically different and it uses the ATAN2, which Alan talked about earlier. It's a logically equivalent equation, except that because the ATAN2 takes two arguments, that allows it to resolve the ambiguity in the quadrant while still correctly doing the rest of the math. And I don't remember how much of an error this caused. It seems that if I'm trying to remember this from the top of my head, but it was something like a 30 or 35 degree error that quadrant ambiguity was causing for a particular star. But anyway, this is why the equation changed. And so far, out of 51, 52 stars entered in that log, it's only impacted one of those. And should I? Is it okay if I move on and talk about the J factor?
Oh yeah, absolutely, absolutely.
Okay, and so um, the J factor is not very well understood by people, and it's widely mischaracterized what it's doing. But what it's really doing is it's a factor that because we know that the RA the right ascension declination to azimuth elevation equation in the stellarium is making mistakes, and the spreadsheet exactly duplicates those mistakes as far as we can tell. The J factor corrects for that mistake. And I mentioned last week how I first detected that mistake, and that's when I was looking at the big anomaly at North Peak. I realized it's making that error because the bearing was completely off. Is it okay if I move on? Seem to have a hot mic going on here.
Yes, I'm furious.
So, in any case, the J factor eliminates that problem, and I talked about that last week, but it does it in a clever way that I think a lot of people don't understand yet. It raises or lowers the star by shifting the timing. So J factor is a timing adjustment, and it's shifting the star until it exactly matches the altitude predicted by the globe Earth model. And when it does that, that automatically also corrects the bearing. And And so it repairs the incorrect bearing that's caused by the equation errors. And it also corrects for uneven terrain on the peak. And then when it does that to the graph, let me show you a ragged graph. Here's the original very ragged graph. As we perfected this a little, we found out we could fix the bearings and smooth it out. And then we discovered that we can add the J factor and straighten it out even more. Finally, on the newest spreadsheet, it just makes the timing of the globe Earth model absolutely perfect. And that's the angle represented by the green line on the very bottom. And on the globe Earth model, that's what Stellarium would call the uncorrected elevation of the star. That's actually an imaginary concept. You can't measure the uncorrected location. It's a calculated value. And the calculated value turns out to be flat Earth measurement minus e squared over 2r. And this diagram here shows that relationship for all of the angles. So the green angle, called theta sub g here, using Pikes Peak as an example, all these numbers here are the original numbers from Pikes Peak. The 2.2 degrees 4 arc minute theta g is the uncorrected globe Earth angle from the observer's location, as verified by the surveyors, the professional surveyors that RUHIF graciously sent to my house to confirm that that was the correct angle from my house. And then what they do in Stellarium is add atmospheric correction to that. And I found that Stellarium's atmospheric correction is so close to G.G. Bennett's celestial refraction equation that you really can't tell the difference. So the blue angle, theta sub r, 2 degrees 17 arc minutes, that's what a terrestrial theodolite would measure. That's approximately what theta g plus atmospheric correction is. From my house, I think that ends up being 2 degrees 18 arc minutes or maybe 219. It depends on who you ask. But basically, that is the flat Earth angle minus d squared over 2r. Compared to theta g, which is the flat Earth angle minus 2 times d squared over 2r. And then the flat Earth angle is the red one on top, theta sub f for flat, and that's 2 degrees and 31 arc minutes from my house. And this diagram shows them all. It's easy to lose track of the fact that this all started as trying to refute the null hypothesis that the Earth is not a globe, or you could translate that as the Earth is flat. So the null hypothesis assumes the Earth is flat, which means 2 degrees and 31 arc minutes is the one angle that the celestial theodolite could not measure in order to refute the hypothesis that the Earth is flat. And as close as the measurements would allow at the time, that's the exact angle it did measure, which meant the null hypothesis is not refuted, and therefore the hypothesis that the Earth is a globe is false, and the hypothesis that the Earth is not a globe is true. And then here are how Stellarium, this diagram just shows how Stellarium calculates all these angles in reality. So I think that's all I have to say about the angle error and the J factor and this diagram.
Yeah, can you go over how you originally derived it real quick, the J value with the ruler and the peak and the significance of that real quick?
Yes,
Because
and I don't have
because yeah, it's like without a clear method for other people to reproduce it, I feel like it's it's difficult to argue like the correctness of it, I guess is what I'm saying.
and I Yeah, and I don't have a good diagram of that, so I'll just explain what I did. Um, I had a video of star occlusions up on my screen, and I paused the video. I measured from the edge of the screen to where the peak was, and I looked at topographical um, maps and photos to figure out approximately where that was. I measured it in centimeters, and as I recall, I came up with 2 minutes and um, actually, I think it was 2.4 arc minutes per centimeter. So that gave me a measurement standard. Then, as as in the video, stars were occluded on the peak. I measured their their distance from the same edge of the screen, and I always did that from the left edge of the screen, just for consistency. And I calculated um, how far off that was from the peak by subtracting my original measurement from the peak. So if I came up with a negative value, I expected to be so many arc minutes left of the peak. If I came up with a positive measurement, I expected that to be so many arc minutes right of the peak. And in the original diagram, and let me go the original graph, excuse me, not that one, but this one. This one is totally uncorrected. Even in this, you can see that the red line, which is the flat Earth prediction, is the closest to zero of all the measurements. The cyan line with atmospheric refraction on from stellarium and the green line with no refraction correction are both way off from the globe Earth estimate. This is the one where I manually applied those corrections from just measuring it with a ruler on the screen, and that didn't account for uneven terrain. It didn't account for measurement errors, but it got me a lot closer. And then this next one is where I realized, well, I can eliminate all this with the J factor. And with the J factor, I just adjusted to make the green line the globe Earth prediction with no atmospheric correction perfect. And as soon as I made that perfect, it made everything else perfect. So it was that kind of cinched the fact that it was a stellarium error in the um, right ascension and declination to azimuth and elevation formula. Um, it was just making slight little errors that were enough to cause this ripple. And so eliminate that, and now you have this. And today's graph, that's improved even more because by using fractional seconds, it's possible to make it 0.0 deviation. So we can make that green line truly, absolutely perfect. The globe Earth deviation from the predicted globe Earth altitude when atmospheric correction is off, and then add GG Bennett to that, and you get the cyan line up above. And all of that is reference to the flat Earth prediction, which is the red line in the center with no deviation. It's right on top of the um, zero delta line, with the sole exception of that 0.3 from the right edge, where that's labeled Jesse in the clouds. That was a fictitious example. Jesse asserted that this would make anything match the flat Earth angle, and that's proof positive that that assertion is incorrect. If you take a stardust in the cloud, make it use the J factor to make it 0.0, it gives you a wildly erroneous altitude that's very far deviant. But all of that comes from this set of equations that show you what the globe Earth is predicting in terms of subtractions or additions to the flat Earth angle. I hope I answered the question. If not, ask a little further.
All right, so you started with a physical method that was taking the measurement of the peak, like, or like centering it on the center of your screen rather, and then measuring in centimeters using a conversion of arc seconds to centimeters, what the difference is in position in terms of like where the star was when it actually got occluded, and you're taking that offset as like a seconds value to apply to your to adjust to the azimuth essentially is what you're saying, right?
Yes, and that all happened. That all happened. I don't know who's talking over me, but that all happened while I was still looking up the values in Stellarium, and so there were some. Oops, I'm sorry. There were some little deviations, little ripples, which you can see above and below the zero line from zeroing or adjusting Stellarium until the bearing was correct, and plugging looking that up in Stellarium and putting that elevation into Stellarium. That's what caused this little ripple. Oh, it was still a little bit off, but it was a lot closer than this. So
Okay.
this is raw measurements. This is bearing corrected measurements, correcting those bearings manually using a ruler on the screen.
Okay, so the azimuth correction from the difference in the position between the two manifest uh as a timing correction then, right?
So, sorry, I got a vacuum going on next to me, and I give it a second to go off, and then repeat your question, please.
Yep.
Okay, vacuum just went off. So, what was that question again?
The question was the timing difference, or I'm sorry, the position difference, like the azimuth correction, will manifest as like a timing difference, right? Because that's how it's going to change the elevation in Nazi.
Ex- Exactly. When you if you carefully examine the uh, right ascension and declination to azimuth and elevation equation, what you'll find is that really boils down to a small timing correction. And so when I saw what was happening with the bearings being off, I realized that all it takes is a tiny little timing correction to repair that. And so that led to the ruler on the screen, um, manually adjusting it to get the bearing correct, and then looking up what the elevation is and plugging it into the spreadsheet to produce a slightly ripply correction.
Okay. So this analysis is going to be dependent on one's like monitor screen resolution, etc.
Screen resolution, your math ability to figure out uh, um, the deviation per millimeter or deviation per centimeter, however you prefer to calculate it, your topographical map and satellite photo interpretation abilities for identifying where on the screen the peak actually was from the bearing you're watching it. So there's a lot of little error factors, which is why doing it this way is still a little bit ripply. And on this, oops, I clicked the stream instead of my presentation. This is the first version where I had the equivalent of Stellarium built into the spreadsheet, and only here where I didn't have to interpolate things with my eyeballs and a ruler and a calculator and look them up in Stellarium, only then did it start getting this smooth. And then over the days, as I found better ways to fix that and found the quadrant ambiguity, and it finally evolved into this, which is this is like as perfect as we could possibly ever correct these star occlusion measurements, I think.
Yeah, I just suppose the problem is like not being able to link it to a physical process that somebody else could do. because otherwise they would just argue that we're just doing a timing correction to make it
Yeah,
work.
yeah,
And
so I would argue
it's
that
hard to
anybody who
argue
is
against.
smart, I would argue that anybody who is smart enough to do the manual process is smart enough to look at the equations in the spreadsheet and see how they're doing the same thing automatically to much greater precision.
And so these results align with a flat Earth, you would say?
Well, even independent of that, just using just the premise that we went over with the physical occlusions using the true geometric position, the globe makes wildly different predictions that never align with flat Earth. And then even ones that where they tried to force it that conflicts with the celestial refraction answer. So it's like this analysis is just like a calibration method to it that makes it a little more clear, a little more obvious, but it's not it's still an ongoing process for that.
And then
Although,
this slide is showing how globe Earth derives their angles from the theta F, which is the flat Earth angle. So all of the globe Earth predictions are actually fictitious d squared over 2r values subtracted from flat Earth prediction. Or in the case of theta sub r, that can also be expressed less accurately as theta sub g plus atmospheric correction.
so is d squared over 2r the equivalent of accommodating 69 miles per degree? Is that what that is?
That's exactly what it is.
Okay. So when I got it. So I mean, yeah, well, that makes sense.
All right. Well, we got, let's see, about 30 minutes left, give or about 40 minutes left. If before we get into Q&A, Shane or Mike, did you have anything else you wanted to go over? And if not, we'll get into a couple of clips from Shane.
So I don't have anything else, and I think we were going to talk about answers to Jesse's questions. So just cue me up whenever you're ready for that.
Oh, right. Okay.
Well, real quick
Shane, you
though,
want to go? You want to go through the? Oh, go ahead.
so if we eliminate the J correction at all, the raw data that we have prior to that still coincides with flat Earth, the 43 different times over globe Earth, right? It's just what he did with the J value, make it to a higher precision, and he brought it down to within like what 2 to 4 meters for flat Earth once he cleaned it up, and then it was always 100 to 2 meters off for the globe prediction. But even without all of that J factor correction, it's still a resounding win on 43 measurements for flat Earth, even if you take out 3 of like it's a win for all 46 measurements, really, right? So all the J correction stuff is neat, but that's just perfection. That's to get it like perfect.
I agree with Shane's assessment.
Yeah, and it's
All
not
right.
like you're just applying it to our prediction. You're applying it to all three.
Yes, exactly.
No, like you don't need it perfect to win the argument, right? Riding on eggshells, right? So if we have a win on every measurement closer to flat Earth, then just because we make it even closer with with a fixing column doesn't mean that the original results are nullified in any way. As much as you guys are super hard pretending that's the case or whatever, it's weird.
Do these
Remember-
measurements also include the southern hemisphere?
Ooh, great question. We do not have any Southern Hemi participants yet at this time. So if you're an Australian lad or a New Zealand lad or some other uh, south of the
Southern
equator
location.
lad,
Yeah.
hit us up. We would love to get some southern measurements. That'd be awesome.
Thank you.
So the barrier for entry is just, do you have a device that can reliably be synchronized to GPS time when it's recording, so that you can reference your when the file was made and then the frame in which the star was occluded at, and like, can you record at night? That's the barrier for entry. And then can you record? Oh, sorry. Second barrier: can you record your lat and long of your location? And then can you look up the peak lat and long? That's all you need to get rolling. So if you would like to do this, you could figure out all the math and prediction stuff and locate the stars later. You could just go out and shoot, and we could figure out everything on the back end.
Awesome.
I am here with questions when it's my turn. Just let me know.
Will do. Will do. Let me see. Shane, did you want to?
You want to
Go
play
over
the clip,
the-
or you want to just talk about it?
I mean, you can, however you want to do it.
I mean,
I
I
just
don't really
work here.
want to. I don't really want to play the clip. I've watched it enough, I think,
Yeah.
and even getting the
All right.
timestamp. So I'll just link the timestamps when we talk about it.
All right. Cool. Cool.
So which one we talking about? So we're talking about when Jesse redefines our method using his own math, and then continues to argue about that method, and also how he would argue different positions to different people on the same sort of thing, like the 5 hour stream we did last week compared to say this stream here with Mattoon, with these timestamps here on things that were previously addressed, and then of course we have the steel manning of the position and then taking the direct counter that's in there as well. But really, I just wanted to go over how you use math to straw man our position as not arctan of rise over run, and then proceeded to argue and attack, argue against and attack that. Yeah, despicable, dishonest, terrible. That's it.
All right, quick highlight. So if you could just link the timestamps or whatever, we can go over. Actually, we could just put that in a PDF for next week. That's not.
Yep.
We're not going to waste a whole thing on that. But before we move on to Mike's PDF answer to Jesse's question from last week, writing on eggshells said something that I think is really significant and important for this argument for both sides. So he says, no, I think it's great that flat earthers are accepting that we can gain information about the surface of the earth by looking at stars. That's so my boy Copernicus once said that, regarding the apparent positions and motions of the bodies, nothing certain can be said. Any conceptual model that yields calculations is basically, what we're going to use. So in regards to the apparent positions, you can make a conceptual model based off of whatever. And what I showed earlier and what Shane's been working on, if you haven't seen the Ether Cause Prezzies lately, Shane just did a 3-part series on the celestial and terrestrial sphere coordinate system and how they work, how they relate. But we see how they use them and how they related positions of the stars with respect to time to those coordinate systems. The apparent positions, right? So like where you see it, and then they have the freedom to make corrections to adjust where even that position, they say that's not where you really see it. It's really here when you apply the correction. So when you have that freedom, you can make any conceptual model work. What is being distinguished here is using that calculated true geometric position with respect to the initial snapshot of the conceptual model of the celestial sphere relating to the terrestrial. uh, we can reference the known elevations of peaks to make mutually exclusive observations, because as we showed earlier, only the physical occlusion is the cause of why the star disappears, and that was demonstrated also when Jesse went to his location that he used a simulator to find the location for, and the geometric position aligned up with the occlusion and not the celestial refraction position. So all right, Mike, if you want to go get into your questions and answers thing. Oh, so anyway, real quick though, uh, the rhetoric of the Earth measures flat and the Earth measures a globe is just empty rhetoric. Without having an external reference, you can't say how flat it is or how globular it is. So using the only external reference we have, the stars, is something that we should definitely consider and be more open-minded about, because the entire you can derive conceptual models off the apparent positions, but calculating where they're going to be and stuff, that's a whole nother story, and we can actually use that to figure out the geometry of this place, because there should be no geometric relationship to the occlusion timing with respect to the calculated angle of that mountain peak relative to an observer X amount of distance away, because the globe would actually predict that the true position be much lower, and often the celestial refraction will be too high or too low. All right, Mike, whenever you're ready, sir.
Okay, I shared on the stream. I shared, and this is a Google document rather than a PDF. This is my response. I think that was yesterday night, last night. Yep, last night. Um, and you can see it took me a couple of weeks to get around to um, answering Jesse's questions, and that's because I'm practically always um, overwhelmed with dog rescue. But uh, uh, Jesse was very kind and gracious. He thanked me for the answer to a previous question. He asked this new question with my new correction: is it possible or impossible to invalidate your null hypothesis that Earth is flat? Specifically, is there any possible star occlusion timing that would lead to invalidation of your null hypothesis? I say not. Following demonstrates my claim. If my claim is true, that is extremely important. If it's not true, then by all means, please show me a possible star occlusion timing, hypothetical, that would invalidate your flat Earth uh, hypothesis. And my answer to Jesse is and my answers are all in blue. In terms of logical fallacies, you asked what is called a loaded question, one that contains an unverified assumption. You used incorrect terminology and also presupposed an incorrect response to your own question. Starting with the incorrect terminology, a null hypothesis needs to be refuted rather than invalidated. By definition, the null hypothesis, Earth is flat, or not a globe if you prefer that, is the mutually exclusive opposite of your hypothesis that Earth is a globe. Indeed, had the very example you propose next been valid, it could have refuted the null hypothesis. Where your example failed was that it was a cloud that occluded the star rather than a peak, and further analysis will follow your example. And so I'll go into his example first. He said, please let me present a hypothetical star occlusion timing. What if we observe the following hypothetical star occlusion timing? And he gives the data, observation from my house, a specific date and time, a specific star name, and the mountain is right on the peak of Mount Rosa. This is a made-up occlusion timing and would not ever be observed unless there was a cloud bank above the mountain, which caused the occlusion, because I picked a star that's about 3.5 degrees above Mount Rosa at that time. However, there could be clouds and it could get occluded up there. This could come in as a reading. If this should happen for only the star on a given mountain, would your new correction method show that this did not match flat Earth? Or would even this huge cloud caused error result in a perfect flat Earth match? My contention is that if it were observed after applying your correction method, it would still match flat Earth perfectly. Am I wrong? And my response is yes, Jesse, you are wrong. And the following screenshot from my second star log of yesterday's version of my spreadsheet emphasizes that he's wrong. And here it shows Jesse's hypothetical, and I needed to enter a J value of negative 1402.4 seconds to zero out delta J. And for those who may not remember what delta J is, that means there is no deviation between what the globe Earth um, uncorrected star angle is and the angle of the star that was just occluded. And when I do that, that star has a bearing error, which is the delta arc minute column of negative 64.6. So in other words, notice that it takes a 1402 second offset, which is 23 minutes, 22 seconds, to zero delta J. And that when zeroed, the deviation from the true bearing is 6,864.6 arc minutes to the left of where it should be. In terms of degrees, that's a 114.41 degree counterclockwise from the proper heading. Had the peak rather than a cloud occluded that star, it would have refuted the null hypothesis. Since this was an intentionally fictitious example, it failed to refute the null hypothesis. And here's that situation graphically, and I show the graph where you can see the huge negative dip at the point Jesse in the clouds. So um, I used the perfection technique to perfect the globe Earth prediction, which is the green line. And indeed, the flat Earth prediction is way off, so it could be refuted had that been a real occlusion. And then, so I went on to close this response to Jesse with please note the extreme deviation from the flat Earth prediction at the point Jesse in the clouds. Prior answers, that graph, and my spreadsheet answer the remainder of your questions in that particular email. I'm not sure you understand that the purpose of the J factor, which is named in Jesse's honor, is to make the globe Earth delta altitude with atmospheric correction off perfectly match its predicted negative d squared over 2r drop, so that the globe Earth delta altitude with atmospheric correction on, which is acts as the G.G. Bennett celestial refraction equation, is as perfect a measurement as possible, and thereafter to assess whether the chip, wherever the chips may fall, for the flat Earth measurement. And then, contrary to your stated expectation, those flat Earth chips perform very poorly in your contrived example. So no, you can't dial in the J factor to 0.0 and make anything measure flat Earth. And that was because your contrived example failed to meet the flat Earth expectation to the peak rather than a cloud is what occluded the star. Best regards, Mike. So the big dip in the red line at Jesse in the clouds is the refutation of the contention that bogus data can be made to show a flat Earth. Bogus data cannot be made to show a flat Earth. And that was the end of my response.
Nice. We pre-addressed all the bullshit. Or I'm sorry, the answer.
Awesome. Thank you for the update.
So if I could jump, I prefer to be a little kinder to Jesse because despite we all take deviations from the path of light at times. And I think Jesse is sincerely trying to do a good job of refuting. Sometimes I don't think I'm understanding. Don't think I'm explaining what's going on in a way that Jesse could understand what I'm saying. As he's noted before, I tend to ramble. He has a few criticisms of me, and I think his criticisms are valid. So I hope that we can all be kind to one another and not use pejorative comments for each other as we shoot down each other's bad ideas.
Nice. Well said, Mike. And let's see here. So, yeah, like I said, moving forward, we're going to do like things that draw out in terms of like extended conversation that's not really going anywhere. We're going to consolidate those to PDF recaps and stuff moving forward. So this was a recap from a conversation that popped up last week. And what we're going to do, or yeah, now we're going to open it to Q&A. So if anyone has any questions, feel free. And if Jesse, if nobody has any questions, you're cleared hot, as they say.
All right.
And we are gonna end at in what is that, 20 minutes? So use your time sparingly, good sir.
All right. Dr. Heffron, thank you for those kind words. That was mean a lot. Could you hop on my screen share, which I'm about to bring up?
I will do that.
Thank you.
I don't respect
It
Jesse
should be
at
up.
all.
You should see some video, a frame grab from one of my star occlusion videos. So let me know when you've got that up, and I'll start circling.
I've got it up.
Okay, good. So this was from Edith's Hook, the 25-mile one. So right here on the right is the tower, the radio tower. And then we've got El Getty and Prima Gaeti and then 3 cap, all visible. So what I've done here, and I think I sent this to you the other day. So what I've done is, because we've got 3 known stars, or 2 known stars spaced apart on the screen, I can get the azimuth of each of those from stellarium, so I know the pixels per degree in the horizontal axis here. So now I've used the known pixels per degree to calculate exactly how many degrees from the tower, the radio tower, that Algety peaked up over the mountain peak. And from that, then, I know what the true azimuth of Algety was at the moment it peaked up, because the radio tower, of course, has its coordinates published with the FCC, so airplanes don't hit it. And I knew my location, so I was able to use the geodetic bearing finder website to get the true bearing to the radio tower, and then knowing the degrees per pixel, I could get the true bearing to Algety as it popped up. Does that make sense so far?
So, sorry, I didn't hit the mute correctly. It makes sense, but I would dispute your bearings. They don't match up correctly.
Well, help me out. And this is
One
what we
more
all
thing.
need. This is what we all need to work through, because when I did the bearing calculation to the tower, I got this, and when I went into Stellarium and got the bearing to the star, I got this. So, and I got also the bearing to this star at that same time. So where did I go wrong?
What's the bearing of the tower relative to the bearing of the mountain?
Well, the mountain is kind of round on top, so I'm not sure the bearing. In order to calculate a bearing, I need a point, and it's not a pointy mountain, but the tower is a point.
There's a bigger issue here, Jesse.
Did I? I guess I had a point on the last of that sentence.
Jesse, there's a bigger issue here.
Hey, Mr. Stone.
Are you certain?
I've waited for weeks to talk with Dr. Mike. Do you mind if he
Excellent.
and I
I'm going to
then you
spend
and I-
4
and then
seconds and
I
you can
can
deal.
talk all we want later, okay? Is that okay, Alan?
It's
Or
important
is
that
he
you
gonna
handle
just
it here
railroad
before
me?
you
Hey,
continue to
Jesse,
waste your time.
Just calm down real sec. Stone doesn't chime in.
It's
unless
just
it's
one
important.
question.
Go ahead, Stone. Just
Yeah,
hang in
thank
there.
you, Alan. Are you absolutely sure that this is a perfectly rectilinear lens? If not, then fisheyeing will skew your measurement left to right across. And we don't know necessarily that the point you're measuring from the center is from the center of the lens. Where was this cropped? Yeah, that's what I wanted to interject with. Go ahead.
So where did I go wrong, Dr. Mike? I mean, I'm honestly trying to follow in your footsteps here.
So, in addition to the points that Stone raised, you have to know, despite the fact that that mountain's round topped, you've got to look at topographical maps, you've got to look at satellite photos, you've got to figure out where the peak actually is relative to where the camera's looking. And as Stone noted, even with that, even with the ruler on the screen can make mistakes depending on the shape of the lens, depending on many other factors. But I don't agree with any of the bearings you have on this diagram. They're all wrong, every single one of them.
Well, now hold on. I mean, you can't say that, because I literally went into Stellarium and I can bring it up. And if you go to this date and time, this is the bearings you'll get within the 1 time second step resolution. So
Maybe you weren't listening about the whole reason for the J factor that Stellarium was reporting bogus data to us, and it needed to be corrected. So it was a matter of correcting Stellarium to give the right angle at the right time.
well, what is the right angle for Algety at this moment in time? I mean, am I even if you think I well, so if I calculate, so you're saying you don't think I calculated my bearings correctly to the tower? I mean, I was very careful.
I think you calculated all your bearings wrong, and in the database, I have a 3 seconds earlier time than what you show on here. Um, so this must have been three
Oh,
seconds after Algetty rose from the
okay.
peak.
I moved the video forward a few seconds so that it showed up really good. Because
Yeah, I
when
did.
it's half occluded, it's you know not very
Yep,
bright.
I I just wanted to make that disclosure that I've got 3 second different timing, and then unfortunately, it looks like I've also got. Oh, here it is. At that point in time, I showed that the actual azimuth is 109 degrees, 54 minutes, and 3 arc seconds.
For
Seconds
Algetty?
later.
Oh,
Yes, for Algetty.
is that your corrected or your raw? Your uncorrected?
That's corrected. That's the whole point of the J factor is to correct it for the errors that show up when we try to measure these things manually.
Okay, but see what's important is that somebody other than you can do this procedure, because until other people can do the procedure correctly, it's just we have to trust you, and that's wonderful, but we need to do it ourselves. So um,
So you can look at the spreadsheet to figure out how to correctly do it. If you understand the math to do this, you can easily understand that math. It will lead you step by step of how to do it exactly correctly.
well, I tried though, but because look, I went in, I calculated the true azimuth angle or the true bearing for Algetty, and it did not need correcting. So this is
Your assertion that it doesn't need correcting means you're totally missing something, and I can't tell you exactly what that is. You're misunderstanding something. I don't know what it is.
okay. So what bearing? What do you think the true bearing of occlusion was for Algetty?
So, like I said, that was 109 degrees, 54 arc minutes, and 3 arc seconds.
So if the bearing to the tower is 109.15, it would not have even been in my camera. I would not have seen it. I wouldn't have even been on frame if it had been at 109.45, right? Because look,
I
this
know
is
nothing about your camera. I don't know the width of it. I don't know what kind of lens you have. I don't know what distortions you're looking at. There's too many variables for me to figure out what's wrong with your measurements, but they are wrong.
well. Can you? How do you know they're wrong? Yeah, did you check them, or are you just saying they're wrong because they don't match flat Earth?
I'm saying they're wrong because they don't conform to the technique used in the current spreadsheet, and that spreadsheet has proven itself for all kinds of stars to be accurate, and it refuted your contention that it can be dialed in such that anything looks flat. So I think this is the pointless argument you're making because you haven't given us enough information about your camera, your lens, how you're making the measurement, the width of the screen. We need a lot more information to figure out what you did wrong. And I just have no idea what you did wrong. But the correct angle of Algetty 3 seconds earlier than what you show, at that time it was 109 degrees, 54 arc minutes, and 3 arc seconds.
Well, would you be willing to, when you get a minute, go over this? I mean, I checked really carefully. I very carefully calculated the true bearing to the tower. I counted the pixels very carefully. What you need to know about my camera is in the text overlay here. The position of Algetty at this moment in time was 109.15.15, and the position of the tower was 109 or 109.37.1. So, and also 3 cap is up here, so you can tell what the zoom of my camera is. It's pretty strong. It was actually hooked up to a normal telescope. But let's just put aside for the second that you're claiming that my measurements are wrong, even though you have no evidence of that. is my method basically correct? In other words, first I get the tower, I get the the location of some recognizable landmark on the occluding mountain, so that I can measure right to left distance on the screen, and I take the observer location. Then I use a true bearing calculator to calculate that, and that gives me the true bearing to the recognizable landmark, in this case the tower. And then I figure some way to make sure that I know how many, degrees per centimeter on the screen, or degrees per pixel, or whatever, so that I can have my horizontal scaling. And then based on the true bearing to the tower and the number of pixels to the star, I then can calculate the true bearing to that star, right? Am I on the right path so far?
So
Real
you
quick,
started out, you missed step
10
one.
10 minutes
Uh,
left. Go ahead.
Yep, Alan described step one really well, which is center the peak on the screen, and you admitted you don't know where the peak is. And if you don't know where the peak is, you can't make any measurements relative to the peak, because when you look up the bearing, whether it's in NOAA or movable types, they're giving you the bearing to the peak, and that's what you're trying to determine the offset of these stars from. Um, so you failed at step one, and you have no idea where the peak is, and that's probably why all of your other measurements are wrong.
Well, why couldn't a radio tower that's been carefully located and recorded be the peak? Why couldn't it be it is the peak. Why couldn't I use an artificial peak as long as it's at a known location? What are you saying? The method would not work on a tabletop mountain, and even if there was a radio tower there?
Yeah, the technique works perfectly fine on Pikes Peak, which is pretty much tabletop. But I and helping flat Earth guys try to use the ruler technique, I noticed they're measuring stars that occluded way below the peak, off on the slope of the mountain, and we can't really tell where the mountain is on this photo. We can estimate. It's kind of interesting that the tower appears to be lower than the peak. So how is that? That's got to be distorting any measurement made relative to that tower. I think you're just making so many amateur errors on this method you're using that it has no hope of correctly determining the actual bearing error.
Well, if I know the exact latitude and longitude of the tower and the exact observer location, then I can calculate the exact bearing to the tower, right?
Only if it were aligned with the peak, but you can tell from this photo the lights on the tower are lower than the star, which means it's closer than the star. And that's going to change where it appears to be. That's kind of the same perspective or apparent location error that the celestial theodolite is designed to eliminate in the first place. So no, you can't do it the way you're doing it. You have to know where the peak is, not where something on the peak is.
Well, why? Why can I not? I mean, the peak serves no purpose except as a recognizable landmark, and as long as the tower doesn't move between one day and the next, why could I not? Why do I? And in fact, I asked if I knew the latitude and longitude of the tower and the observer, could I calculate the bearing to the tower? And you said no, not unless I know where the peak is. Why would there even need to be a peak for me to calculate the bearing to a tower when I know the location of it?
So I hate to pull a Sheldon Cooper on you, but I can explain it to you, but I can't make you understand. If you don't understand why that's a problem, I cannot make you understand.
Well, I think everybody here knows that if you have you could have 2 points on a perfectly flat plane and still calculate the bearing between them. You don't need a mountain peak. If you've got point A and point B, you've got a bearing. I think everybody here knows that. So saying that I can't understand why I can't calculate, I don't think anybody here understands why you say that we can't calculate a bearing between two known points without a peak.
Is there anybody here that can explain to Jesse in better words than I used why a radio tower that's much closer can't be used as a point of reference to something that's being occluded by a peak that's far in the distance?
Well,
What do you
I
mean
would
closer?
ask. I would ask that what type of tower is it? How high is the tower? And why do you think a tower is not constantly swaying? Because
Well,
I've worked on towers and the top of towers move. They don't ever settle.
that was
Yeah,
a
I don't think
Right? So it's
that's
not a fixed
Why are we
object.
shifting focus to the tower instead of the star being occluded by the mountain peak?
Well, you got something stationary, right? Which is the mountain that's not going to move. We know it's not going to move. And
well,
you avoided it to reference something that can sway.
And to answer the question, why are we discussing the tower, is Jesse is trying to substitute his own method for knowing where the peak is. And knowing where the tower is not the same as knowing where the peak is that's occluding the star.
well, I'm using the tower as an artificial peak that's recognizable, and because there's no highly recognizable
Is
peak on this
is the
mountain.
tower occluding the star, Jesse?
Well, I guess
Do you need me
if
to repeat the question?
I guess if it's not possible to measure the bearing between, or to calculate the bearing between 2 points, two known points, unless there's a peak, then I guess geometry has broken down, and
I think you're straw
nobody
manning
in the
now.
world can actually do this procedure, because nobody is allowed to know how to do this procedure, because clearly, as I've demonstrated here, if one actually does the procedure, it would still give globe matching results in certain instances, as this one does.
So
and
I'll repeat.
You're,
I'll repeat step one. Look at where the peak is on a topographical map on satellite photos. Locate where the peak is in your photograph. Not not locate where something else on the peak is. You need to know where the peak is so that you can reference everything relative to that bearing.
Okay, well,
and real quick, because we're going to wrap up in 4 minutes, I wanted to recap on something that you said. So in certain instances, right? Now, keep in mind, we're consistent with our method using the true geometric position, whereas you're relying on celestial refraction to explain the differences for the other ones. And the one instance where you use the simulator to figure the like the elevation difference in the mountain expected elevation drop versus the observer's elevation and and their distance, using a formulation of that ratio, you use the true geometric position instead of the refracted position for the globe measurement, which would contradict that the star would still be visible at that time via celestial refraction. So it's like even though you tried to like demonstrate a globe measurement, you actually contradicted the globular explanation to an insane degree. Like what we're arguing over now is like secondary points of explanation and trying to figure out like the calibration of it. So just to be clear on like what's been measured so far and where we're at in the conversation. Anyway, go ahead and continue.
well, I'm not sure what there is to continue. I went 25 miles away plus change. I filmed Algety peeking up from behind this hill with a very recognizable landmark on that same hill at the same distance. And I calculated the bearing to the recognizable landmark and the star, and it all checks out. It gives
yeah, but Jesse, you ignored the part where he said you ignored step one. Can you address step one?
What's step one?
Really?
You don't know it either, do you?
Really?
See,
Yeah.
that's the problem, is nobody's telling us what.
Hold, no,
Step one
hold
was
on.
being aligned in, okay, go ahead.
Knowing where the peak is.
I mean, I could rework this math. I drew an indication where the peak is. I can find it on, but it's not gonna.
I thought you said you didn't know where the peak was because it's round.
It's got a point that's a little bit higher than the rest. Obviously, I can find that. It's not going to be as accurate as
Now
the
you're
tower,
changing
but
your. Good job, Jesse. You've done well tonight.
I mean, like, you can see, it's going to be the same. I'll just be, instead of referencing the tower, I'll be referencing a little bit over, but it's going to be the same problem when I count the pixels and the degrees between the peak and the star. It's still the star's azimuth is still going to be very, very, very close to what Stellarium said the azimuth was at the time of appearance. And the time that it appeared at gives the globe results when you then move Stellarium to the peak with the atmosphere off. So there's no reason to correct this particular star, and yet he's applying over a minute of time correction in his spreadsheet with no definable excuse.
We are at our time limit for this celestial theodolite update. We will follow up. I assume you're gonna follow up with this with a PDF, so we could follow up next week, so we can get more in depth on it.
I think I already sent this to you to send to him.
Did you?
Yep, and I emailed it to him also.
Okay, so then we will continue this one on next week then.
Alrighty, thank you.
Yep. Thank you, sir. All right. Dr. Mike, thank you. Gio, thank you for hosting. Muchas gracias, senor.
Yep. Yeah.
Shane,
Cheers.
thank you for rebroadcasting. Of course, Galley, Beast, thank you guys for moderating, keeping track of the chat. And if anyone has any questions, Flat Earth or Globe, tag Galatrax or myself, and we will add those to a question and answers thing for next week. So I do have one. Oh, I need to turn it into a PDF. I do have one from last week. Some of the questions that were asked, I will convert that now and upload it. And then next week we will do the same, and we'll just kind of follow the same thing, and we'll just upload the collection of PDFs so that everything can be cataloged and tracked, so everybody can stay up to date on what the arguments are, what the methodology is, and the state of progress of things. And thanks for everyone for participating. Thanks for everyone who is going out there and getting measurements, man.
Can I just ask a quick question on the outro? Is this channel being put on YouTube or anything? Can we put a link in the chat? Maybe so some people can go watch it that just got here late, maybe like me.
Yep, it's
Yep, I got it.
Yeah, thank you, Gally.
Thank you, appreciate it.
Thank you, Gally. All right, and quick note: everyone that bought Ether Cause merch and lifetime memberships and supported us, your guys' merch should be arriving. You should have already gotten it, or it should be arriving very, very soon. And with that,
I got mine.
Go ahead and close out. Nice. Oh yeah, you got yours. That's awesome.
Yes, it's awesome. It's real super high quality. Specifically, the sweatshirt hoodie is solid, man. It is well built, thick, heavy duty. Love it.
Nice, dude. Glad to hear it. Yeah, Kat knocked it out of the park. She found a nice local place that has everything here, and she found really good. You know, they make really good stuff. So it was awesome. All right. Well, we'll go ahead and close up. Shane, whenever you're ready to end the stream, sir, if you're there. Oh, he's headed back now. All right, I can end it on YouTube. Give me 1 second.
Thanks for the show.